Hello, everyone, and welcome to London PyTorch Meetup number 11. And today we're going to hear from two speakers, from Misa and from Chris. Akinkunle also was eager to teach us something about Bayesian parameter optimization, but unfortunately he just tested positive with COVID and he's not feeling great today. So we'll hear from him at a future event. And as usual, to begin, we'll ask Paul about some updates and what's going on his side, and then we'll proceed with the talks. Paul?
Thanks, Karina. Yes, so I'd just like to add my greetings to everybody, especially those that have joined us from far afield. And unusually, I haven't got very much to say this time round, but I would give a quick update on the fact that we're making good progress on opening a London AI campus. And I guess my ask on this at the moment is probably anybody who knows of potential corporate sponsors. That would be very interesting. So this campus will be for startups and scale-ups and also for AI training. It will certainly benefit the ecosystem very much. And so anybody who works for a large corporate, a Microsoft or whatever, and feels they might be interested in sponsoring that, please let me know. That's it from me. Thank you very much.
Thank you, Paul. And yeah, a big shout out to people who are joining us from other continents, which is exciting. That's the benefit of having online meetups. We're able to connect people across the globe now. And our first talk is from Misa Ogura. I hope I'm pronouncing it not too bad. And yeah, Misa, the screen is yours.
Cool, thank you, Karina, and thank you for inviting me to speak here. I have put a link to my slide deck in the chat. Hopefully you can see it, tinyurl.com/blah, blah, blah. You'll be able to follow along or, skip ahead or go back a few slides at your own pace. But with that, let me present my screen. Okay, can everyone see the slides?
Yes.
Yeah, great. Okay, let me know if there's any issues with the slides, but I'm gonna go ahead. So yeah, I guess I'm gonna start with kind of explaining the title, Seeing Through the Eyes of Neural Networks with FlashTorch. Neural networks are often sort of considered, I suppose, black box because of the way the model is trained with millions of parameters. And I wanted to sort of create a toolkit around it to make visualization of what the neural network is paying attention to easier. So that's the FlashTorch, which is the tool I created. I'm Misa Ogura. I'm originally from Tokyo, based in London now. I was a cancer cell biologist before changing my career to become a sort of enter the world of programming about 5 years ago. Currently, I'm a research software engineer at BBC R&D, and I'm also a co-founder and CTO of Women Driven Development, which is an organization where we run hackathons for women and non-binary people in tech to get together and use technology for good, and also to learn from one another and share experiences. So unfortunately, I won't be able to stay afterwards, but you can find me in all these places. You can click on any of the icons, and yeah, hopefully, if you have any questions or anything, please reach out. Feel free to reach out. Cool. So before I'm going into FlashTorch and what it is all about, I just wanted to kind of give a brief overview of kind of what I'm going to be talking about, which is convolutional neural network. So in order to understand convolutional neural network, we need to understand first the convolution bit, which is an image processing technique. So it's a process by which we apply a filter, which is usually a small square matrix, We apply this over an input image, an area of input image, to calculate the weighted sum of that area. And so you can see in this example, on the left-hand side is an input image, and the result of convolution is on the right-hand side, which is an output image. And we use this technique to detect features such as edges and curves. And in normal sort of image processing, and what the features that we're looking for, they're predefined. So we say, oh, I want to detect vertical edge on the right-hand side, then we would use this kernel that you're seeing, which is also another name for a filter. But we would use right Sobel kernel and create this image on the right-hand side to detect vertical edge. So convolutional neural network is that combines convolution and deep neural network. So you can see in this figure a very simplified version of architecture of a CNN. And the most important thing to remember is that the features which were predefined in normal convolution are learned during training. So in this case, we have a task to classify an image into 4 possible classes, and the features that are useful in achieving this task or performing this task well is learned during the training and fine-tuned. So coming back to the question of, so how can we explain the output from CNN, which is quite tricky, again, due to the number of parameters that involves and often very large architecture. So feature visualization is an area of research to address this question. It has evolved kind of driven by the demand to make neural networks more explainable. And we do so by looking through the eyes of neural networks. So if you aren't familiar with the area, there's a brilliant series of articles on this still. So I highly recommend you checking them out. But for the purpose of this talk, I would like to focus on one particular area within feature visualization, which is called salience maps. So saliency maps in computer vision in general, they show you an area within an image, which area within an input image, which is the most interesting part. So saliency in sort of human visual perception is something that makes certain regions within an image stand out and grabs our attention. And the method to create this saliency maps for CNN was introduced about 7 years ago. And essentially, what we can do is to focus on an output of a particular class. So, for example, in this case, it could be a class output of the boat. And if we calculate the relationship between this label or value for this label and input image pixels. So each pixels within an input image, that relationship and the class labels. So essentially more sort of mathematically defined term, if we calculate the gradients of an output class output with regards to input image pixels, then we can establish the connection between these two. And the important thing to remember is that if a pixel within an input image has a positive gradient, it means that it has positive effect on the label that we're focusing on. Okay. So I sort of, when I came across the field of research, and I got really excited and I wanted to try it out by myself, but there wasn't sort of a sort of ready to go tool available, at least for PyTorch models that I had lying around. So this was the motivation behind creating FlashTorch. It is an open source feature visualization toolkit, which supports Torch Vision models out of the box, as well as custom PyTorch models. And it's available to install via pip. So now, for the latter half of the talk, I'd like to show you some examples of how you might want to use FlashTorch to make your CNN more explainable. Okay. So FlashTorch comes with a set of utility functions to help you kind of prepare and transform images if needed. So I am now here taking an image of the owl and apply transformations so that at the end of the transformation, I have a torch tensor with a certain size ready to be inputted through CNN. Next up, I need to create a backprop object, and this is where sort of the meat of the FlashTorch comes in. So I'm loading a pre-trained model, AlexNet, from Torch Visions, and I'm passing this model to a backprop class to instantiate the backprop object. And what's happening behind the scenes here is that the FlashTorch is registering custom functions to model layers so that we can grab the intermediate gradients out of the computational graph as it flows through and being calculated. And intermediate gradients are something that PyTorch usually don't expose to users, and that's where FlashTorch helps achieving. Okay, so once we've created a backprop object, now it's time to visualize the gradients. So all we have to do is to invoke a visualize method on backprop object with the input image and the target class index passed in. Okay, and so what we see here are 4 subplots. Obviously, the first one is the input. The next 2 plots are showing you the gradients that the FlashTorch sort of grabbed out of the computational graph. So you can see that, especially with an overlay at the very end of the plot, that this round head and eyes of the owl had the most sort of the strongest positive effect on the network's prediction that this was a great owl. Okay, so that kind of makes sense. I think, I would think that these are also kind of quite characteristic thing about this bird. But what about other birds? Are they, would the network look for the same thing? And the answer is no. If we ask network sort of, what it was paying attention to when it was sort of looking at the peacock, image of a peacock, you can see that those characteristic feather pattern pixels around it had the most strongest effect. And in case of a toucan, actually, it was this magnificent beak that it has. Okay, so we've kind of seen when model is pre-trained, we know it works well on certain images, and it's kind of nice and all, but can it be more useful? Is FlashTorch actually useful when model is not getting things right? And the second demo is to sort of there to kind of explore this question when neural networks is performing poorly. So for this, I'm using transfer learning, which is a form of knowledge transfer where in machine learning in particular, a model developed for one task is reused as a starting point for another often related tasks. Okay, so what I did was to grab a model which is pre-trained with ImageNet dataset, which has 1,000 classes. It's readily available from Torch Vision. And then I swapped out the last layer, which is a fully connected layer, from 10,000 classes to 102 classes. So I've only just swapped out the last layer. It hasn't been fine-tuned, and I called this model, for the sake of the talk, untuned. Then I took this untuned model and trained it with a flower dataset, which contains 102 flower species. And I call this a tuned model. So when I first assessed the performance of the untuned model, it had about 0.1% accuracy on the test dataset. And obviously is much worse than just guessing it by myself. So it's kind of, at this point, I think it's really easy for us to then jump onto training. But I would like us to stop here and inspect and use FlashTorch to see why it might be getting things so badly. Okay, so for this example, I'm using foxgloves as an input image. Okay, so the same thing. I've loaded the trained model, swapped out the last layer and called it untuned model. Then in it, I've instantiated the backprop object by passing the model to a backprop class. Now, what we can see from here is that the network seems to be paying attention to sort of the general maybe shape of the flower. You can see the pixel images around flower cups are sort of lit up. And if you think about it, there are many flower species that has a similar shape. So it looks like the network doesn't really know what to look for, right? So that's kind of, I guess we can start to explain. Now, after training, the tuned model achieved above 98% accuracy, which I was really happy about, because certainly better than I would do, much better. But then again, not stopping there, I think is quite important. How is it that it's better? What is it that it's seeing now that it wasn't seeing previously before training? So I want to create a new similar visualization, but using tuned model. And the result is the next slide. And the difference is striking. What we can appreciate that now network is paying attention to the most distinguishing pattern of this flower species, which is the mottled pattern inside the flower cup. And being able to visualize like this, I think it's quite powerful. And with feature visualization, I think we're better equipped to focus more on the mechanism of how and what neural networks are learning, which helps us to kind of diagnose what and why the network is, performing the way it's performing. But also, it kind of allows us to spot and correct biases in algorithms in times where it's making predictions that is not desirable. So I think with this, we can kind of step forward a bit in understanding and trusting systems driven by AI. So with that, that's the end of my talk. I have links here to the GitHub repository with FlashTorch, and also I've created some Google Colab notebooks so you can try it out without installing anything. And yeah, as always, suggestions and contributions are very much welcomed. So thank you very much.
Thank you so much, Misa. That was a wonderful talk.
Thank you.
And while other people can either ask a question in the chat or just unmute themselves and jump in, I'll take my chance to ask you the first question, is whether you ever looked at the evolution of those attention maps. So is it quite binary of at first network doesn't know what to look for and then it just finds it? Or is it a very slow evolution from general as a... So basically, can you use it to understand when to stop training, when you got most of the benefit?
Yeah. So whether we're being able to know when to stop might depends on your definition of what the model should be doing. I think in conjunction with, for example, test accuracy, it might help us understand more of what the network is doing, apart from sort of just looking at the accuracy. In terms of the evolution of sort of this saliency maps, you can definitely do that by kind of stopping at sort of, at every 10 epochs or something, and inspect saliency maps from that particular model in time. So yeah, it should definitely be able to visualize the model evolution over time using FlashTorch.
Because it should be useful in detecting overfitting, right? Because at some point you're focusing on the right details, well, right from a human perspective. And then at some point you just find some peculiar pixel location. And it's like, this is good for predicting this based on the training data.
Yes, yeah, definitely. I think I've come across examples where I don't know, it was the model was predicting whether it was a sort of a food sort of recipe detection, and it was saying that it was Chinese noodles, and when you open on the box, it just model was paying attention to like a wok behind it, like a Chinese wok behind it or something like that. So yeah, it's helpful in kind of in addition to the usual metrics we use, with the validation loss and test loss, and I think it will help us kind of understand model performance more heuristically. And there are many other sort of techniques you can use within feature visualizations, not just saliency maps for that.
Yep. So we have a question from Muhammad Assad, and he's saying, have you thought about how this could work for regression models where the output is a continuous variable?
Yes. So in principle, I've never tested it on regression models, but in principle, we can do the same computation on any sort of models using this using calculating gradients. It should be possible. So if you take a regression sort of prediction value and calculated gradients of that against input, then you would be able to calculate gradients. If the input happen to be an image, then you should be able to visualize that gradient just like we're doing here. But yeah, FlashTorch at the moment doesn't support or regression models. But yeah, it's a very good point. And yeah, you should be able to do the same thing.
Cool. So the next question is from Mani, and he's asking, what about the gradient values that PyTorch does not expose to the users? If it changes in the future and becomes available to the user, would that make the tool redundant?
Part of it, yes, will be redundant. So the answer to your question, if the PyTorch starts exposing those gradients, then it will become easier for PyTorch users to grab the gradients. Another thing that FlashTorch tries to do is to create a helpful visualization. So in that sense, it might still be useful. But you can always, plot gradients yourself. And so, yeah, in that case, it could be redundant. But there are other sort of, as I mentioned, there are many other techniques within feature visualizations. And I'm trying to kind of expand FlashTorch to enable users to try out these techniques really easily. So there's another module called activation maximization module within FlashTorch, which does slightly different things to calculating gradients. So that in that sense, it might still survive. But
Thank you.
Hope that answers your question.
And the next question is from Dan, asking whether FlashTorch is set up for dealing with one-dimensional CNNs for things like text classification.
Yes. So with regards to one-dimensional CNNs, there was a feature request from a user. So it didn't used to support it, but now it supports out of the box with just with one-dimensional input. Text classification, no, we don't support it currently. There's a lot of things that I'd like to do. But yeah, there's definitely text classification and visualization of sort of attention mechanisms there would be quite interesting.
Right, and then we'll also have a logistical question from Mark. Where are the samples for people to try something out?
Yes, let me send you a link to GitHub, because that will contain all of the links to Colab notebooks.
Thank you. Looks like Mani already found the link.
Oh, you got it. Great. Awesome. Yes, it should. Yeah, it should be near to the top. Yeah.
And we have a question. Sorry, Misa. Go on.
So just to flag that something up in the Google Colab, try and if you are trying using Notebook, use CPU, not the GPU, because somehow something has changed in Colab GPU setting, and now visualization is not working. Someone posted issue a few days ago, and I'm yet to resolve it. So yeah, please use CPU when you try Google Colab.
All right. There's a question from Sab asking if FlashTorch supports object detection models.
Currently, no. Yeah, the tool is at the moment kind of geared towards classification models, but definitely some users have expressed their interest in applying this to object detection models.
I see.
Well, these are oysters. Yeah.
There is a question from Sanad asking, how much of FlashTorch knowledge as a tool do you need in order to be able to make it DSL ML? I'm not sure what's meant by DSL, but hopefully you know, Misa.
I'm not. Yeah, so I'm not sure what you mean by DSL, domain-specific language. I see. Thank you. I'm not very good with acronyms, as you can see. Okay. Knowledge as a tool. Hopefully you shouldn't need too much. What I tried to do with FlashTorch was that users don't need to learn too much about it and kind of get on with the visualization. So hopefully very little, but yeah, let me know if it didn't answer your question.
All right, and yeah, there's also a question from Mani. Would this technique work with other types of models, not just PyTorch models?
Unfortunately, it's specific to PyTorch, but there are certain some tools available for example, TensorFlow models. I can send it. There's a link in the README, but I can also share here. So for example, this one does similar things, and it's much more extensive than the FlashTorch, what the extent FlashTorch offers. But yeah, so if you have a kind of Keras/TensorFlow model, tools like that is available as well.
Cool. So a question from me, Misa, is there any tools that you'd like any functionality that you'd like to implement if you would have time to work on it? Is there something on your list that?
Yeah, so definitely the text classification as well as object detection models, but also 3D models. So CNN that handles 3D images, that's something that could be interesting in terms of like how to visualize and, yeah. So these things are all quite high up in my to-do list. And yeah, I'm always kind of looking for people who want to contribute or, submit issues or try out with their own models. And reach out with their questions and requests.
Cool. So everyone, you heard it. If you want to, and given how many comments we had in the chat, that it was an amazing talk and really interesting, and the package is of high interest to many people, then please do reach out to Misa using the contact information in the slides, for which there will be a link. And yeah, please do collaborate.
Yes, just to answer the last question from Muhammad, what's the best place to contact? If it's anything FlashTorch specific, probably specifically issues or anything, perhaps on GitHub. Otherwise, otherwise the email that I have, the first slide on the talk. There's a link to. Okay, so there's no link to email address, but on LinkedIn or Twitter, I'm usually on there. Hopefully that's useful.
Yeah,
and I can share my email here as well. It's here we go. So that's the email I use for GitHub as well. Anyway, so yeah.
And also a totally off-topic question. What did you use to make the slides? Because it seems to me like a really good way to share the information.
Yeah, thank you. It's really good. It's a actually tool that comes with Jupyter Notebook. It's called NB Convert. I just typed it in there, and you can create into interactive slides like this, or you can create sort of PDF from just a standard Jupyter Notebook. And I usually prefer if I have a code snippet that I would like to share. You can customize it in many different ways, but out of the box, it's still useful as well.
Looks amazing. I'm surprised that not more people are using it.
Yeah, thank you for asking. I always try to advocate for NB Convert because it's such a great tool. It's a great presentation.
Yep, I loved it. Thank you so much, Misa.
Thank you. I'm afraid I'm gonna have to shoot off, but please do get in touch. I would love to speak with you all about it.
Have a nice evening, Misa. Thank you so much for joining us. And
thank you.
Yep, it would be a big round of applause, but unfortunately, world.
I'm gonna just cut myself. Okay. Okay. Take care, everyone. Speak soon.
Thank you so much.
Bye.
All right. So now that we learned about attention in the models, we'll hear from Chris from Kagenova, and he'll take us to the VR world.
Oh, hi. So I'll share.
Yep, the screen is all yours.
I'll share my screen. Can everyone see this?
Yep.
Okay, great. I think that talk actually fits quite nicely with what we were doing, because you'll see some of the same diagrams in this. So what I'm going to talk about is a paper we just submitted to ICLR. So this is the first time it's being presented, because we submitted it on Friday. And it's going to be about our new spherical machine learning models, and obviously, as Karina said, we're a VR company, so how we're applying it to VR. Some of the other authors of the paper on the call, so in the networking later, maybe if you have any questions, you can also just ask them and ask them about this paper. I'm just going to tell you a little bit about Kagenova. We are trying to apply machine learning in areas where currently they cannot be applied, or they can be applied but with not great outcomes. So this involves developing new machine learning techniques and applying them to 360 photos, 360 videos, and other places like that. This involves making new geometric learning techniques, and as we'll see in the talk, we're specializing in spherical machine learning as a sub area of geometric deep learning, and that has a surprisingly large amount of places where it can be used. And as we'll see in the talk, it's all to do with rotations, and whenever you have rotations, spherical machine learning probably has a role to play. Now, we're applying this to VR. A lot of the members of our team are from astrophysics or generally more right in physics. And the reason why there's this connection here is because the mathematics used in spherical machine learning, a lot of it originated in astrophysics and quantum mechanics. In fact, Roger Penrose won the Nobel Prize today, and he was one of the developers of part of the mathematics that's used in some of the spherical machine learning techniques. So there is a real connection between physics and spherical machine learning. Okay, finally, I'm just going to tell you about our products. So we've applied machine learning to VR. We have Copernic 360 and Copernic Worlds. They both bring 360 images and videos to life. So Copernic 360 works on any particular one 360 image or video, and we do depth estimation, and then we make a 3D model, and we allow the user to move around that 3D model. Copernic Worlds then extends this to tours. So if you have multiple photos of an area, again, we can make the 3D model, and then you can walk around this larger area, and you can really see the space that you've captured. Potentially more interesting for you guys is FullPyAI. So this is our package that we're developing, which includes a lot of the layers that you'll see in this talk. And we're developing it, and if anyone's interested, please do get in touch. Okay, so now I'm going to talk about the paper, efficient generalized spherical CNNs. You'll recognize this diagram. I just wanted to bring it up in the same way to really hammer home what the important features are of planar convolutional networks and why they therefore work so well, to then make the connection between spherical machine learning and what are the similar properties that we want our spherical machine learning models and layers to have. So a planar CNN, you have a filter, and then you do this kind of element-wise multiplication and then summation to get your feature maps. And that you translate the kernel along all the different pixels, and the result after each translation is the result in the new feature map. And this gives us what's called translational equivariance, and it's a really key feature of planar convolutional neural networks. The point is that we're trying to learn features about this horse's head, for example, and so clearly these are the activation maps of some of the network, and you can see there are certain features of the horse that are clearly being picked up by the CNNs. Now, if the horse's head was to be, say, over here, the same features exist, and the convolutional network can easily pick them up, and they would just exist on a different place in the feature map. And this translation, the fact that the same features are then picked up just in a different place is what we call translational equivariance. And it allows you to then just learn what a horse looks like once, rather than having to learn what a horse looks like over here and everything. You just learn what it looks like once, and then it'll work across the image. The similar thing that we have in spherical networks is rotational equivariance. So if you see this kind of sphere being rotated, if you learn what India looks like once, if it's rotated in a different place, it still looks the same to the network, and it still understands that. How does it actually do it? So as we went before, you have to do this element-wise multiplication, and then you sum it, and then you translate it by an integer number of pixels across the image. And by doing this integer translation of pixels, you do the convolution. Unfortunately, this is not possible on the sphere. So if you look at different pixelizations of the sphere, no pixelization of the sphere will allow you to have this property where you can do convolutions accurately by just translating a kernel. This comes because if you look at, say you define a kernel here, and then you wanted to rotate it round to the equator to see what the activation would be at the equator, and these pixels clearly would not line perfectly with these pixels, and you would get pixelation artifacts in your convolution. So the way we get around this is to use harmonic space. I'm just going to briefly go into what the connection is in Fourier space and then go into harmonic space. So when we're doing this, we do a Fourier transform. So a Fourier transform, you take an image, you apply this Fourier transform, and you get the Fourier coefficients. And the Fourier transform basically looks at different causes and signs that you need to make up the image. There are loads of different uses for this, but the one that we're kind of interested in at the moment is how to do convolutions. So if you want to do a convolution in Fourier space, you want to convolve f with your filter psi, you just have to do an element-wise multiplication of the Fourier transforms of your features and your filter map. Then you can just do a Fourier transform back and you'll get the answer. You can do the same thing in spherical static, except you now have to use the spherical harmonics, which act exactly the same way as you use the complex exponentials in the planar space. And again, you do something which is kind of similar, kind of element-wise multiplication is slightly different, but ultimately it's the same kind of thing. So in this way, we can build up spherical convolutional layers. You do a spherical harmonic transform, this kind of element-wise multiplication, and then an inverse transform. So we start in real space and we can end in real space. And this works brilliantly. We can now get perfectly equivariant convolutions. So the next step, we need our activations. So what activations can we have, and how do they work on spherical images? The naive and obvious thing, and a very effective thing, is to do pointwise activation. So this is like the ReLU. So you apply the ReLU to this output tensor, and in an individual pixels, it zeroes out or lets the signal through. Unfortunately, we need to check that we still have the same feature that we had before. We still want this activation itself to be equivariant. And unfortunately, as we showed in our paper, that Hello?
Now we can hear you again.
How long have you not been able to hear me for?
About 10 seconds.
Okay. Was I on this slide?
Yes.
This slide?
Yeah,
Okay.
As you transition to the next one.
Okay, so this is so I was saying that unfortunately the ReLU isn't, and any other pointwise activation functions aren't equivariant, and this is our metric for equivariance. And we're showing here that the convolutions to machine precision are equivariant, but unfortunately the ReLU isn't. And this comes back to the same point we were talking about before, which is to do with the pixelization. So as we're applying this ReLU per pixel, as the pixels are different shapes and they correspond to different areas on the image, they have different effects over different parts of the sphere, which affects their equivariance. Now, the same solution, similar kind of solution applied to the convolution can apply here. So instead of doing our activation functions in real space, now we want to do our activation functions in harmonic space. So what we do is we use tensor products. These, I'm not going to go into the details of these. These are kind of coefficients which we have to compute. But basically what we're doing is we're multiplying together our tensor with some coefficients. And in fact, in some sense, we're getting a kind of like squaring term in our on our activation to make our activation function. And these kind of tensor products naturally occur from quantum mechanics when you're trying to couple angular momentum. Now, this is one particular tensor product which you can do, and didn't load. Okay, reload. Apparently having some problem. No, that's quite significant, these bits that are. What if I just, oh, why is this? That's very strange. You can see it here, but you can't see it here. Why has that happened? What if I just try and refresh the whole thing? Aha, this looks promising. Aha, good, okay. So where was I? What I was saying was we can do these tensor products, and this what I'm showing here is just one particular tensor product. And Condor et al. Showed that if you combine all the possible tensor products that you can do, you can create what they call the Clebsch-Gordon transform. And so you combine a tensor product of the L equals 0, so this is one part of the spherical harmonics of your feature map, and you combine it, you do a tensor product with it with another part of the spherical harmonics of your feature map, and you get some output maps which are now an equivariant combination of these previous ones. And this works incredibly well, and you can show that it is perfectly equivariant. We have if you see that L is the number of pixels that we have in the kind of theta direction, this Clebsch-Gordon transform scales as L to the 5, so it's quite prohibitively expensive, and in a lot of the cases it really limits its use case because of that. So we were looking at ways in which we can speed this up, and we were looking, well, there's what they've done here is they've included all the possible tensor products that you could have. And so if we consider graphs that have the possible tensor products, so say we want to go from, we're going into L equals 2 here, and we can have a tensor product from L equals 0 and L equals 2. That is showing, we show it and that in a connection in a graph from 0 to 2. So what we have here is a plot of one of those graphs. So this is the tensor products that would go into L equals 4, and it's all the possible connections that you could have. And as I said before, the graph with all the connections has a scaling of L to the 5. So what we want to do is say, what could we remove some of them? Now, we obviously want as many of these connections as possible, because the more connected the model is, the more ability it has to collect together the information from different parts of the image and then come up with a strong representation. So we wanted to use what's called the minimum spanning tree. So the minimum spanning tree is if there is a path from one node to another, the minimum spanning tree will still have a path. It might just not have all the connections. So for example, in here, you can get from 4 to 2 directly, but in our minimum spanning tree, you can get to 4 to 2, but you have to go via 6. So all the paths exist, but not necessarily all the connections. And now we've reduced the scaling to L equals 4. Now we thought, well, what could we do even better than that? Can we remove any more of the connections? So then we started to logarithmically choose different connections to remove. And that reduced our complexity to L cubed log L. This is a significant improvement, and it removes a lot of the computational cost. One of the other problems that this network has is this part is kind of their convolution term, and they have a very large amount of parameters in here. And we did a kind of a clever factorizing of these matrices to reduce the number of parameters. And I won't go into the details here, but it significantly reduces the parameters in the same way that depth-wise only convolutions reduce it in MobileNet, if you guys are familiar with that. So it's all very well good to have the experiment theory, but let's see how it does on experiments. The first experiment that we looked at is a kind of classic benchmark in spherical machine learning, which is MNIST on the sphere. So we've taken MNIST, which is the digits, hand-drawn digits, and then we project them onto the plane, and we create these spherical, like people have drawn 0 on a ball, basically. And we set up a neural network with the kind of layers that we've been talking about. We use these convolutions. We do actually use a couple of ReLUs, and we have the understanding that actually at the beginning of the network it has less of an effect. But later on, we use the tensor products to really get the equivariance in these high-level features. I'm just going to talk you through this table because it's quite interesting, and it's got some. When I first saw that people were using this, I thought, oh, that's kind of, it's almost like bragging at this point, how these kind of networks can do. So there are 3 cases, and it pertains to whether or not you're going to rotate the balls which the images are put onto. So on the left here, we have like non-rotated images, and on the right, we have rotated images, rotated spheres. So the first column is non-rotate, rotate. So where we don't have rotation, with the test and train set are both of this type. And we can see that planar networks do very well. And this is basically normal MNIST. Planar networks and all the spherical networks do quite well. If we then go on to the rotate, so this is where we try and effectively, you could potentially augment rotational invariance into your data by essentially teaching the planar network what a 0 looks like up here and what it looks like up here. And if you do that, it gets 90%, and the spherical methods then win by showing that actually if you inherently have this equivariance and invariance to rotations, you naturally do better. Then the next step is a kind of showing off technique where you don't rotate the inputs, but you rotate the training data, but you rotate the test data. And our model, as it's perfectly invariant, doesn't care that the images initially weren't rotated because as far as it's concerned, they're all the same. And then we have a couple of other cool experiments which we've shown it on. This one is an example of how spherical machine learning crops up in physics and chemistry naturally. So the idea of this problem set is to regress the atomization energy. So that's the energy it would take to break all the bonds in this molecule. Now, the molecule and the physics of the molecule is exactly the same, regardless of how the molecule is rotated around any individual atom. And so if you build a model that understands inherently and is invariant to the rotations of the molecule around that atom, then it will naturally have all the physical properties that you would expect it to have with regards to rotations. And so we make a kind of simple model and we apply it to this data set. And this is the RMS on this regression problem. And we show that with significantly fewer parameters, this increased equivariance and factorization of the convolutions into fewer parameters means that you can really get good results on this data set. The final data set we've been playing around with and we put in this paper is 3D shape classification. So the problem here is we get given a mesh, and this is an example of a Star Wars fighter. You're given a 3D mesh, and you don't know which orientation the mesh is in. And because it could be in any orientation, it would be good if your model was variant to those rotations. So people have created a kind of a way of taking these meshes and creating sphere representations of them. So that you put a sphere around the model, and you take cast rays into the model, and you take properties like how far is the ray, what angle does the ray create with the normal. the mesh, and so then you create these spherical representations. And again, we apply a very similar model, and with dramatically fewer parameters, about half as many parameters or even more. Sometimes we get state-of-the-art results in the classification. I won't go into these metrics because they're really quite specific to the particular competition that this was. But if you're interested in this, we've been working. This is our 4Pi AI package. This has got all the layers that we've been developing and working on. Unfortunately, it's in TensorFlow, but we're also working on making a PyTorch version. It's not public at the moment, but if you want to collaborate, you want to get your hands on any of this, please do get in touch. We're really happy to look for and work with people who have any problems which they think rotations might be important. If you're interested in working with us or any kind of collaborations, please do get in touch. There's an email address. I'll post this in the chat, I guess. Just include something that kind of says that you're from the machine learning area, because we get people who come from various different areas. It'd be nice to streamline you to the right people straight away. Cool. Thank you.
Thank you so much, Chris.